Okay, we're ready for the next presentation, and Joel Tropp, and he has written a monograph on the concentration in inequalities in the convergence of the matrix graph things, matrix things. The inequalities are always interesting. Random matrices are always interesting, and you've got to move away from the edges, or you bound the faraway things. And I started to read your monograph, and it is readable even for an economist. So I hope that's taken as a compliment. I mean it that way. Also, he's from Texas. I was hoping he would wear a Texas hat.
I'm wearing boots. Is that good enough? All right. Thanks for the introduction and the invitation. So to begin, I'd like to tell you where I'm from now. I'm in the Department of Computing and Mathematical Sciences at Caltech, and we have on our faculty computer scientists, applied mathematicians, and control theorists in this department. And so we've all been grouped together because of the sentiment that modern problems in applied math require computing and math, and also the dynamics and control perspective that the control theory community provides. Okay. Now, this research I'm going to be telling you about today is in a long tradition of work in which you take an established field of mathematics and append to the beginning the word applied in the hope of creating a new field, or the word computational in the hope of creating a new field and identifying new questions and new tools that arise from the interaction between the old field and the question about what you do with it. So, of course, the most famous example of this is applied mathematics, which has been pretty successful. But there are more recent vintages, including computational topology, which has seen a tremendous amount of energy over the last 5 or 10 years, and we'll be hearing about that a little bit later from Gunnar Carlson. And so today I'd like to tell you about the interaction between random matrix theory and its applications, and some of the new questions I think that arise from that nexus. Okay, so first of all, what is a random matrix? So this is straightforward. It's just what you think. It is an array of numbers which are random. Okay? And one important aspect is that the random numbers in this array may not be statistically independent. Okay? So they could have very complicated interactions with each other. They might be independent, but in a lot of the interesting applications, that will not be the case. So I have here in captivity an instance of a random matrix. So one of the things I'd like you to notice here is that some of the entries are not so random. So there are a lot of zeros in here in a very clean pattern. And those are not random at all. At the same time, the other entries are populated with random numbers, but you can see that there's some strong dependencies among them. So this matrix appears to be triplet, except where I've zeroed it out. And so even though it's random, it's not that random. And these kinds of issues are actually quite common when you look at the random matrices that arise in contemporary applications. Okay? So I just want you to keep that in mind. All right. Now, what is it about random matrices that are different or special that necessitate a field of study apart from the field of probability, which studies, of course, random variables, or even random vectors, collections of random variables? And the reason that random matrices are different and interesting is that they act on vectors to produce other vectors. And as a consequence, square random matrices have eigenvalues and eigenvectors. general random matrices of singular values and singular vectors. And if we think about the map as acting between two normed spaces, we might also be interested in the operator norm of that random matrix, which will reflect not only the randomness in the matrix, but also the geometry of the domain and the codomain. Okay? And so all of the questions about random matrices that are really fundamentally random matrix questions concern their actions as operators. Okay. I mean, you can also ask questions about arrays of numbers that are really just treating them like they're long vectors, but those have a different character. Okay. Now, for classical random matrices, I'll tell you a little bit more about what these guys look like. There's a huge literature on this subject that dates back, depending on whom you ask, at least to 1927. Even though that is very well documented in a wide range of books from multivariate statistics, mathematical physics, operator theory, high-dimensional statistics, and a book more from the mathematics point of view. Nevertheless, there are not so many references available that will tell you about the random matrix I showed you on the first slide. Okay? So let me tell you a little bit more about where random matrices come from so you can appreciate some of the history. They're almost 100 years old now, although Peter Forrester told me that he traces the first instance to work of Hurwitz on invariant integrals over the orthogonal group, which dates in some form or another to the end of the 19th century. But the place that this really seemed to emerge as a subject of independent interest was in the statistics literature. So this smiling gentleman here is John Wishart, a Scottish statistician who was a student of Fisher. And he worked out in this complicated formula here the joint distribution of the eigenvalues of a sample covariance matrix for a vector of jointly Gaussian random variables. Okay, so that's a mouthful. But at least in that setting, you can write down the joint distribution of all of the eigenvalues of the random matrix, and that was one of the earliest models for multivariate data. And of course, random matrices have served for a very long time in statistics as a model for multivariate data. And this seems to be one of the first places where the distribution of the spectrum was computed explicitly. Okay. The second place that I'd like to mention, this is not the second instance where where random matrices arose, but what really accelerated the field into, I think, the consciousness of the mathematical community was the work of this smiling gentleman, Eugene Wigner, who appears here in his Nobel Prize photograph. So Wigner wrote a very famous paper in 1955 about a random matrix that he took as a model for a heavy atom undergoing a slow nuclear reaction. So for small atoms, you can compute these things explicitly. When the atoms get big, well, the physicists weren't quite sure what to do. And so Wigner surmised that if you just wrote down a Hamiltonian for the reaction that had all of the symmetries that you believed were present in the reaction, and then took it to be random subject to those symmetries, then it might serve as a reasonable model for how that process behaved. And in the mathematics paper, he abstracted that to study a symmetric matrix whose entries above the diagonal were independent, uniformly plus or minus one random variables. So this was what's called now a Wigner matrix. And he showed in this paper, which I've exerted here, that the limiting spectral distribution, the distribution of the eigenvalues of this matrix as it becomes big, follow the semicircular law. And beginning with this work, there was a huge development, especially in mathematical physics, of random matrix theory, and this is where it really started to filter into the mathematics community and develop a life of its own. Now, I want to emphasize that here, too, the random matrix is actually pretty special. Although the distribution of the entries can be changed without affecting the distribution of the eigenvalues, nevertheless, all of the entries are independent. They all have the same mean. They all have the same variance. and there's a symmetry assumption in place. And as a consequence, this model is good for describing Hamiltonians, but it's not necessarily so good for describing everything else. Okay, so there's another early example that I like to mention, which is numerical linear algebra, where random matrices were used to model floating point errors in LU factorization. A beautiful piece of work by Hermann Goldstein and John von Neumann. And then these ideas started to filter into other areas, such as graph theory, asymptotic convex geometry, number theory, and even an operator theory in the 1980s. And so really started to spread throughout mathematics. One thing I'd like to emphasize is that in almost all of these cases, people were really looking at random matrix models that had a huge number of symmetries, and from my point of view, are very special. Now, because they're special, you can say a huge amount about them. They have beautiful mathematical properties, their connections with a wide range of mathematical fields. Unfortunately, that also means that they're not so useful for contemporary applications. So just to indicate the range of places where random matrices are now applied, I made a short list of some of the areas that I've seen these ideas applied. So these papers are chosen at random, non-uniformly. People use random matrices in numerical linear algebra for developing fast algorithms, for computing approximate matrix decompositions. They use it for fast kernel summation. They use it to build models of which variables are important in uncertainty quantification problems. They're used as models in high-dimensional statistics. They appear in econometrics for the same reason, and a huge range of other areas. And so as you can imagine, in a lot of these situations, the random matrices that come up maybe actually depend on some data or an input to an algorithm, and they're not so arbitrary and they don't have so many symmetries. And so to address the kind of questions that are coming out of these fields, you now need to ask new questions about the random matrices, or to ask the old questions but develop new tools to answer them. And that's been the goal of the inquiry that I'm going to describe here. So let me define a random matrix model as a class of random matrices that admit a unified analysis. This is kind of vague, but it's just intended to give you the idea that you can package some class of random matrices together, and you can understand them all at once in terms of some small collection of summary parameters that you hope are easy to compute. Now, I would assert that when you're talking about random matrix models, especially if you have this wide range of applications in view, there are a few desiderata that you'd like to obey. So first of all, you'd like the model to be flexible. So it should describe all sorts of stuff. So here's an example of a random matrix model that is not flexible, the identity matrix. Okay? I'll tell you more about that in a moment. The model should be easy to use. So you should be able to calculate the summary parameters very efficiently and directly, and the model should be powerful. The analysis should actually give you a reasonable understanding of what's going on here. So if your random matrix model is the identity matrix, it doesn't describe very much stuff. On the other hand, it's very easy to use, and it is very easy to analyze. You get very detailed information about its spectrum. You know that the eigenvalues all equal 1, and every vector is an eigenvector. Okay, great. But it's not useful because it doesn't describe anything you actually care about. And in particular, it's not even random. But I take this facetious example to show that there really is a tension here where you can build a model that's ultra flexible like the one I put on the first slide, which is a random matrix is an array of numbers which are random variables that may well be correlated with each other. That's an extremely flexible model, but not so easy to use, and the analysis is pretty hopeless with that degree of generality. And so somehow you're trying to balance all of these goals at the same time, to find a model that describes a bunch of things, but at the same time is easy to use and where you can get reasonable answers to your questions about the spectral properties. Okay? So the classical random matrix models as I've said, are things that have a lot of symmetries. So, for example, the GOE and GUE matrices are roughly what happens if you take a uniformly random orthogonal matrix or unitary matrix and add it to its transpose or conjugate transpose. Okay? So these matrices have a huge number of symmetries. We can understand their spectra in great detail, work everything out explicitly. There's really a beautiful world of mathematics surrounding these matrices. There are Wishart matrices and Jacobi matrices and some other extensions where the matrices have the same structure, but maybe you allow the distributions to be a little bit weaker. And one of the interesting things that comes up here is that these extended models where you allow different, variability in the distribution. Nevertheless, these models have spectral properties that behave a lot like the invariant models. This is called a universality phenomenon. And people have used this universality phenomenon to argue that you can actually use these extended models and that they are useful beyond the narrow scope of the assumptions where they're posed. I would actually dispute that claim in the sense that even though these models behave the same way as these models, that doesn't mean that they actually model the things that you care about. And there are a lot of other extensions. Again, there's a lot of beautiful mathematics here, but again, I would assert that when you start doing numerical analysis, building randomized algorithms, trying to do statistical modeling, you're going to run into examples that are not so friendly, that do not behave the same way, and for which you need new ideas. So here's an example of a random matrix that comes up all the time in contemporary problems. You have a fixed matrix here. I just want to emphasize that this is a very structured matrix, okay? And it is by no means random. The way we obtain the random matrix is by deleting random rows from this matrix to obtain some other matrix. So where might this come up? Well, it might come up if you were, I don't know, trying to build a Monte Carlo Markov chain sampler that involves picking some subcollection of your data points at each step. We heard a little bit about that earlier. It comes up also in a variety of numerical algorithms where someone hands you an input matrix and you subsample it randomly. Okay? The classical random matrix theory tells you nothing about this example. And yet, at the same time, it's one of the ones that's actually most common these days because people love to subsample their data. And so, if you want to understand what these matrices behave like, even in a coarse way, you need some other tools. So, I come to my thesis statement. I learned in high school that every paper or every talk should have a thesis statement. And my claim is that the applications we encounter now really do demand new random matrix models. So I'm going to give you some examples of random matrix models that I think are more useful for contemporary problems, and a few examples of the applications that you can study using those models. Okay? So the first one is what I call the independent entry model. So this is pretty straightforward. You have a random matrix whose entries are independent random variables. We will often assume that they're centered, but the key point is that we do not assume the variances are the same. Okay, so this comes up a lot. I'll give you an example in a moment. And this is different from like the Marchenko-Pasteur type matrices because in those examples, the variances all basically have to be the same as each other. And by allowing different variances, we can actually see a wide range of phenomena that do not occur for the classical model. Okay, so there's a beautiful theorem about this model from just last year by Ramon van Handel and Afonso Bandera. So they argue that if the entries of this random matrix are regular enough, so they have light tails, then you can compute the expected spectral norm of this random matrix, the maximum singular value, as follows. This is a typo. You take the square of the matrix with the transpose on the second guy, take the expectation, and then take the norm. There should be an expectation inside here. Then you take the square of the matrix with the conjugate transpose on the first matrix, you take the expectation, then you take the norm. This is like an expected square of something zero mean. It's like a variance.
Are the variances fixed?
Yeah, they're fixed in advance. I mean, they could be random variables, and then you would, this would be a random quantity. But part of the power here is that they can be anything you want. And they could even, depend on each other. So you might condition on the variances and then compute the. But the entries do need to be independent, conditional on that. So the strong claim in this model. Okay, so these things here are like non-commutative L2 norms. The expectation of the square of something that is zero mean. And the interesting thing is that random matrices have two squares, not one. And we need both of them in this connection. The second quantity is the maximum variance of any of the entries squared. And this theorem asserts that the expected norm of the matrix is controlled by the square root of the variance plus the maximum variance times a logarithmic factor in the dimensions of the matrix. And this result is essentially sharp for most examples. And it can be extended beyond the setting where the entries are sub-Gaussian. Okay, so it's a beautiful result. It describes a pretty wide class of random matrix problems that come up in applications. And one that I think is particularly nice is the analysis of the stochastic block model, where you're interested in the adjacency matrix of a graph, where the graph has roughly two components that are well connected, and between the components there are relatively fewer edges. Okay, and so if you look at the adjacency matrix of that graph, it's got higher variances on two diagonal blocks and small variances on the off-diagonal blocks corresponding to the links between different communities. And if you want to analyze a random matrix of that form, you can't use the Marchenko-Pasteur type result. You really need a result that allows different variances. And so Efron-Stein has used this result to very good effect in that context and obtained sharp results for the problem of recovering the communities in the stochastic block model using a semi-definite program. And again, having this type of random matrix model is absolutely essential in this application.
These variances, Zij can equal to 0.
Yeah, some of them could be 0.
It can also mostly be 0 is also okay.
Sorry, one more time?
It doesn't matter how many zeros you have.
Nope. Nope. Whether the result is sharp does depend on the relative size of the variances. So if they're extremely heterogeneous, this result might not be quite right. But if a polynomial number, roughly, of the entries are somewhat large, then this estimate can't be improved. So there's a lot more detail in the paper they wrote on this subject. But so independent entry model, relatively new, very useful. Efron-Stein has a nice paper out on the archive right now that describes a number of other applications of these ideas. Okay, now we come to another model that I particularly like, which is the independent sum model for a random matrix. This is in parallel with one of the most basic models from all of probability theory, which is an independent sum of random scalar variables. In this case, we move from a sum of independent random scalars to a sum of independent random matrices, and I'm going to assume that they're centered, so they mean 0 without loss. So this is a distribution-free model. The only thing I'm assuming is independence and that each summand has mean 0. And then beyond that, we might like to use basic information about the distributions to say more about the sum, but in particular, I'm not specifying anything about the summands beyond the independence and the centering. Okay. So this model is innocuous, but it's extremely powerful. And I wrote an entire book about this, as has been alluded to. And here is a sort of typical theorem about this random matrix model, which indicates that, again, in spite of the generality, you can analyze every matrix that you can shoehorn into this form using one result. And again, we have the matrix variance. There should be expectations inside both of these norms. So this is a non-commutative variance, matrix variance. And now we have a second parameter, which is the expected maximum squared norm of any summand. the square being inside the expectation. Okay? These are all spectral norms here. So this reflects roughly the maximum size of one of the summands. And the result here states that the expected norm of the random matrix is proportional to the square root of the variance. It is also proportional to this upper bound, the maximum size of a summand, and then there's some small logarithmic factors here. Okay. So again, if we can shoehorn the matrix into this model, we make two simple computations of these parameters. We get a bound for the expected norm, and this bound is essentially sharp. So V and L both appear in a lower bound for this quantity, and you can even show that the logarithms can't be removed if you look at worst case examples. So even in the best case, you still have to pay for V and L on the left-hand side. Okay? So you can't improve on this bound substantially, and yet it applies to this model that describes all sorts of things. So for example, that random row submatrix can be written as a sum of independent random matrices, each of which determines whether a row is there or it's not there. So each of the random matrices corresponds to one row. The row is on or the row is off. And using this kind of result, not precisely this result, you can bound the extreme singular values of the random set of rows from a fixed arbitrary matrix, which again is a problem that comes up ubiquitously now. It can also be used for more algorithmic applications in machine learning. So for example, there's a paper from ICML from last year where this tool precisely is used to study the random feature method for approximating the kernel for kernel PCA or kernel canonical correlation analysis. And the reason is because you can write these approximations of the kernel as a sum of independent rank 1 matrices. And using this kind of result, you get a very short analysis, which is nearly sharp. And it gives you evidence about the performance of these algorithms and justification that these algorithms are effective. And again, if you're trying to rely on classical random matrix theory, you will get nowhere on these problems. You really do need these tools. I would like to mention that this particular result, which I call the matrix Rosenthal inequality, has a very long history. And the earliest results of this flavor are due to Françoise Luce-Picard from 1986. And there is a long sequence of works. And it's really only been in the last few years where it's been nailed down in this detailed, complete form, where everything is sharp. But nevertheless, it does have a long history.
So does the number of terms come in?
It plays no role because it's hidden inside the variance. And also, if, for example, these have tails, you're going to pay for the number of them through the maximum, right? But this is also interesting.
Infinite weird stuff happen?
Sorry, what?
Can you make it infinite? Or?
Sure. I mean, if it doesn't have 2 moments, it's going to be infinite. If it does have 2 moments, this works. So one of the other reasons this is an interesting result is because it works for heavy-tailed examples. And again, you have a matching lower bound, so it tells you that in the heavy-tail case, you may well have to suffer whatever that upper bound parameter is. Okay. So here's an even more general model. So this is what I call the independent input model. So a matrix from this class takes independent random variables, x1 up to xr, as input. These can be in any kind of space you want. They get munged together, and out comes a random matrix, which may depend in a very complicated way on these inputs. So you might imagine that you can't say anything about this kind of random matrix, but that's actually not true. I'm also going to assume that this is centered just for simplicity. You should be able to compute the mean of the random matrix as a matrix, otherwise you can't use these tools. And the reason is that random matrices tend to concentrate around their mean, just the way that scalar random variables do, provided that they don't depend too much on any one of the inputs. Okay? So if this function isn't too irregular, so changing one of the inputs doesn't change the random matrix very much, then there are concentration type results that tell you that this thing has got to be close to its mean, which I assume to be 0. And in fact, that assessment is correct. And there are a number of results that build on this idea. So here's a result that I proved in 2012 for this model. And for simplicity, I'm going to assume that the random matrix is also symmetric. So if the sum of the squares of the changes in the random matrix, so if you change the ith variable, if the squared difference can't change by more than ai squared, then you can bound the norm of the random matrix in terms of the sum of the squares of the changes. Okay, so this is a lot like the bounded difference inequality for functions of independent random variables, but it's matrix flavored now. So the total sum of the square, worst case sum of squares of changes, controls the expected norm of the random matrix. And so this is a very general result. It applies to very general random matrices. And you can use this, for example, if you want to study the confusion matrix in multi-class classification problems. And again, these random matrices are nuts. I mean, they come out of algorithms that you maybe don't have that much control over. And as a result, you don't know anything about the limiting spectral distribution, the eigenvalues. You can't apply any of this classical theory. And yet, at the same time, you can still get useful bounds on the norm of the random matrix using these kinds of tools. Yeah?
What is the rate of the error? Is it the same as the exactly inequality?
Sorry, one more time. What is the what?
What is the rate of the error? You're saying E of z is less than equal, or almost.
Yeah, there's a constant that I'm suppressing. So the tilde just means absolute constant. But what? Oh, you can also develop probability bounds using classical concentration results for the reason that the expected norm concentrates around its mean. You can prove them in the, so in this setting, you actually get concentration that looks like e to the minus sigma, e to the minus sigma squared. Sorry, the probability that the norm exceeds t is something like e to the minus t over sigma squared. Okay? You can prove that directly, or you can use a scalar concentration inequality coupled with this mean estimate. The real value of these results is that they tell you means, not that they give you tail information, although you can also extract tail information using the same methods. But scalar concentration typically gives you better tail bounds, which is why I focused on the means in this talk. Thank you. Okay, and let me show you one more result that's even more general, or actually more powerful than the last one. So this is a very recent result with Daniel Paulin, a postdoc at the National University of Singapore, and Lester Mackey, who's in the statistics department at Stanford. And so again, this is for the independent input model. So we're assuming that the random matrix is symmetric and centered. And what we're going to do is we're going to ask what happens if we change one of the random variables to an independent copy. We compute the square difference between the matrix and its the version with one of the variables changed, and then we take the expectation conditional on the original version. Okay, so this is some proxy for the variance of the random matrix. This is, in general, smaller than the bounded difference quantity sigma squared that I showed you on the previous slide, which is sort of like an ultra worst case of this. And the claim here is that the expected norm of the random matrix is controlled by the size of this random variance proxy. Okay? And so this comes up, for example, if you have random matrices like a compound sample covariance matrix, which is something of the form like Z transpose B Z, where Z is random and B is fixed. And so again, these are complicated random matrices. There is a little bit of analysis in that particular case, but if you want to understand these things, you really need these kinds of contemporary tools. So I got a little obsessed with this subject, and I've written a few papers about it now. But if you want to understand the most basic ideas connected with the independent sum model, I have just published a monograph on this subject, which is freely available on my website. And it talks about some of the basic matrix concentration inequalities, which give you useful bounds for the expected norm of a random matrix. And it gives a lot of examples from statistics, machine learning, optimization, combinatorics, and other areas, so that you can see how these tools are widely applicable and are useful. And my aim with this work has really been, even one step back from what Mike was talking about in terms of methodology. So what I'm interested in here is the method behind the methodology, the tools that we need to develop and analyze these randomized algorithms, to develop and understand high-dimensional statistical estimators. And the hope is that by working with these new random matrix models that have the flexibility to describe the kinds of problems that come up in applications now, that we'll be able to really develop a new class of methodologies for big data. Thank you. It's all true, in short.
The accuracy of the result as a function of the ratio, like of the matrix size?
Yeah, so typically the matrix size comes up in that log factor. So you'll pay a weak dimensional term, so the logarithm of the dimension. Otherwise, the role of the dimension is not really present. There are a lot of examples where the dimension shouldn't play a role at all, but these tools are not sharp enough to get those bounds. Yeah.